Hello, math humans. We're going to do 1.5a today. We're going to be talking about analyzing functions. Our objectives are that we're going to find the zeros. We're going to do it both algebraically and graphically. We're going to discuss intervals of increasing and decreasing, and then we're going to determine our extrema. Before we get started, just a couple of things to remember. So my domain, which oftentimes is a shortcut, we just use the capital D, is the set of defined x values. And remember, when we report domain, we use interval notation. Range is going to be the set of defined y values. And again, the expectation is that you'll use interval notation for that as well. Remember, when you're reporting domain, you read it left to right, and range is read from the bottom up. Alrighty. For our interval notation, remember that a square bracket is called a closed bracket, which means that the end point is included. And an open bracket means that the end point is not included. Whew. Alrighty. The other thing that we want to remind you about is the vertical line test. And remember, that's how you test graphically to determine, sorry, I was having a brain fart, to determine if a relation is a function. All right, so as we start today, we're going to first talk about this weird concept of zeros. And the reason that it's weird is that we often use words interchangeably. So sometimes they're called x-intercepts, and sometimes they're called solutions. The tricky part is we report these differently. So for reporting zeros, I could just list them, -3, 5. If I was talking about my intercepts, I would say x-intercept colon, and then I would do 2, 0, -3, 0, and 5, 0. Because when we talk about x-intercepts, the expectation is that you will report in ordered pairs. And if I ask you for solutions, I can just list those as well. So it's important that you remember what your notation is going to look like. All right, so let's just jump right in with our first example. So for example 1, it's going to say find the zeros analytically. And remember that analytically means let's do algebra, woohoo! And then we're going to also do it graphically. And we love playing with our graphers. So we're going to do a couple of these. For the first one, the equation is going to be f of x is equal to 3x squared plus x minus 10. The fastest way to solve for x, if possible, is to use your favorite F word, factoring. I'm going to do this with guess and test. So this is 3x and x. The factors of 10 are going to be 5 and 2. And so I need a positive number, so I'm going to put a positive 2 out there because 3 times 2 is 6. And then I'm going to put the -5 in here. A -5 and 2 is a -10. And then 6 minus 5 is 1. So that means that x is going to equal 5/3 and a -2. So now if I do this graphically, I'm going to cover up the equation because it works better for you to see my grapher over here. I'm going to put in my first equation, 3x squared plus x minus 10, and I'm going to do a zoom 6. And remember, if I'm doing something graphically, the expectation is that you will sketch the graph and then label the points that are important. So now I'm going to do second, calculate 0, and I'm going to go to the left of my 0 and hit enter. Then I'm going to go to the right of my 0 and hit enter, enter, because the guess is not important. And it tells me right here that that's a -2. That's what we're looking for, so that's what I'm going to label. If I find the other one, second calculate 0, I'm going to go to the left, but this time the left is under, so I'm just going to the left side, and then I'm going to cross, enter, enter, and that one is 1.667, so I'm going to round to 3 decimal places, and then I'm going to list my answers. So it's a -2 and 1.667. So that was actually pretty easy. It wasn't a complicated graph. All right, next example, move my paper back down so you can see. So this will be B, is g of x is going to equal the square root of 10 minus x squared. So remember, if you're finding zeros, that's finding an x-intercept, and that means that y is equal to 0. So I'm going to take my handy-dandy equation, set it equal to 0. Now I'm going to square both sides to undo the radical. 10 minus x squared is 0, and then I'm going to solve this equation. X squared is 10. X is equal to plus or minus radical 10. Every time you take an even root, it generates 2 solutions. This is a quadratic, and so it's important that you take and show that you have 2 solutions. Radical 10 doesn't reduce because its factors are 2 and 5, so therefore this is in its simplest form. So then I have reported well. So now let's put this one in our grapher. So let's go back and kill what's there. And we had second square root of 10 minus x squared. And again, I'm going to just hit enter because I just did, sorry, I'm going to quit and I'm going to hit graph. Woo, there we go. And so I'll bring it up and show it to you in just a second. But it looks like on the calculator, see if I can get in there so you can see it, that there is a gap at the x-axis. So that is called grapher failure. Poor grapher. So grapher failure. The graphics on your calculator aren't always adequate enough, we're not playing Game Boy or anything, to show you exactly what's going on so we can do some investigation work and we can look at our table. So I'm going to do second table. And I'm actually going to change my table to change in ones and see if I can get it to be happy. Nope, it's not going to do it. All right, so let's see if I can do it this way. So see at the top where it says plus for change table. So I'm going to do plus and tell it I want it to enter in ones. It's still not going to do it. Sad day. All right, so we'll take it from here. Notice we have the square root of 10. So look right here, at negative 3.001, I have a defined value, and then if I go down, at 2.999, just the other side of 3, I have a defined value. At 3.999, I have an error, and the error means that's undefined. So this is my negative radical 10 and my positive radical 10, or I could list the values, but we haven't really found them in our grapher, but this shows you that the values are actually defined. All right, so that's good for that example. Sometimes it's harder to use the grapher than it is to do the algebra by hand, but sometimes we need to try to do both. All right, and then I have one more of these. I'm going to have h of t is equal to 2t minus 3 over t plus 5. This is a great function. We will spend some time on these later, but this is called a rational function. And it basically means that it is a function divided by a function. If you'll remember from previous math classes, this is going to create a vertical asymptote, however you choose to say that weird word, okay? And remember that you set the denominator equal to 0, and that tells you where your vertical asymptote is, okay? And I'm just going to sketch the graph because we're going to do this kind of both ways. So at a negative 5, you always have to sketch in the asymptote. This tells me that my horizontal asymptote is going to be y is equal to 2. And we will talk about this later, so I'm not going to spend any time on it right now. I'm just going to tell you how I knew that. All right. And then the graph, the branches are in those two locations. All righty. So the other thing that's cool to note about a rational function is that this is the x-intercept. So the x-intercepts in a rational function come from the numerator. And it's actually super simple, so t is going to equal 3/2 because it's already factored for me. So I can get a ton of information by already doing this. And my graph is a little bit crappy because I sketched it by hand before I found this. So technically 3/2 is like here. My graph would do that, and this value would be 3/2. So now let me show it to you in your calculator. And you need to be a little bit careful when you put rational functions in your calculator. The entire numerator needs to be in one parentheses, and the entire denominator needs to be in parentheses. So I'm going to do 2 minus 3 divided by t plus 5. Remember, it doesn't matter what the variables are because a variable is a variable. I am going to do a zoom 6 on this one. Oh, look at that. So pretty. Now, the calculator is not going to show you that there's a vertical asymptote over here at x is equal to a -5. It's easier to find that algebraically, but you can notice that we found my x-intercept to be 3/2, and that's about 3/2 right over here. So that's kind of cool. And then I could find that I could do second calculate 0, and there's the left, lucky me, and then move just to the right a little bit, inner, and it would tell me that it's 1.5. So it's really kind of nice to be able to use both your algebra and your grapher. All right, the next thing that we're going to talk about is, let me find a different color, analyzing a function. So let me move my paper up a bit. And we're going to talk about analyzing a function. So when you're asked to analyze a function, I will give you the prompts. So Bain will give you the prompts. And then all you have to do are answer the questions. Lovely. All right, so the first thing that we're going to talk about is increasing and decreasing. And these are always in intervals. All right, so this is the first part of analyzing a function. So let's say I have a cute little function. It's going to be kind of weird looking. It's got a decreasing, it's got a constant, and an increasing. And I'm going to kind of draw some lines on the graph so you can see where things change. Okay? In the left portion, we'll call this section 1, section 2, and section 3. In section 1, as x moves to the right, the y values are getting smaller. It's also kind of handy if you think about it like slope. The slope of this particular portion of the curve is kind of negative. So we would say that the function f of x is decreasing, and we're going to go from a negative infinity, and I guess I need to give you some points. So let's say this is a -2 and a +2, okay, to a -2, all right? When we're talking about decreasing and increasing intervals, we don't know exactly where the graph changes from one particular feature to another, so it's always going to be open brackets, always. And then if we talk about portion of the graph in the second region, that is constant. Notice that all of the y values are the same, so we would say f of x is constant, and it's going to go from a -2 to a +2. And remember, we always read left to right, so when we're talking about math, we talk about math left to right. In the right-hand side, in section number 3, notice that it's kind of like the graph has a positive slope. And so we would say f of x is increasing, and it's going to increase from 2 to +infinity. Another way to think about increasing is as the x values go to the right, the y values are going up, and that would be increasing. All right? So now let's do a couple of examples so we can kind of hone this concept in. So this will be example 2. And I'm just going to give us a graph with some numbers on it so we can talk about where the graph is increasing and decreasing. So my graph is going to look kind of like this. That's a cool one. The vertex is going to happen at a -1, and that guy's going to happen at 1. And before I do this, I tend to draw on my graph. That guy has a positive slope. This guy has a negative slope. And this guy has a positive slope, and those arrows actually help a lot as you try to write what's happening. If my slope is positive, the function is increasing. If my slope is negative, the graph is also decreasing. So if I were reporting, I would say for this function, it is increasing from a -infinity to a -1. Remember that it's open brackets because I don't know exactly where the change takes place. It's also increasing from 1 to positive infinity, and it's okay if you use a union and make one complete statement. This particular graph is decreasing from a -1 to 1. So that was actually pretty straightforward. All right? So now let's do the next concept called extrema. And I'm actually going to use the graph that we have on our paper as we illustrate it. There are a couple of different types of extrema. I can have an absolute extrema, or I can have a relative. Absolute means nothing goes above or below, and relative means in a local area. Okay? And then we can have maximums and minimums. So I'm just going to talk about this particular function that we have right here. Notice on this left-hand side that the function goes down forever, and on this side the function goes up forever. So there would be nothing absolute. So this point right here, and I'm going to write it up there, is going to be a relative maximum. Sometimes people would call it a local maximum, and depending on the book that you're using, you see both sets of words. This little guy over here, if you're looking at just kind of this local area, would be a relative minimum, or we could call it a local minimum. It wouldn't be an absolute max or min because this graph goes forever down and forever up. All right? So let's look at another couple of graphs. So let's say I have a cute little parabola. It has an absolute minimum. And then typically, let's say this is at a -2, I would say at x is equal to a -2 because often they want to know where does that occur. Let's do a different one over here. So maybe I have an upside down parabola and that point is a 3. This would be an absolute maximum at x is equal to 3. Alrighty? Another cool example is the absolute value function. So there's my absolute value function, and you can't see all of it because it's hiding. So this would be, let's say at 4, an absolute minimum at x is equal to 4. So extrema aren't that difficult. All right, I think that's probably enough for today. We will do some more examples when we get to class tomorrow, but I will see you soon.